Alright, hello. I just wanted to take a few minutes in this screencast and discuss reference states. So reference states is something that's defined for convenience, but it's something when it's introduced can sometimes cause confusion for students. The thing to keep in mind is thermo is a field of differences. If I think back to our first law of thermodynamics, right, we had delta U is equal to Q plus W. So all the way back in our first law, all right, the quantity of interest was delta U, a change in internal energy. Right? And so thermo is all about differences. If I think back to all the property relationships we worked out, right, what we worked out are a bunch of differential expressions. Expressions for dg, dh, ds, and so on and so forth. Differentials because what we ultimately want to calculate is changes in those properties for a given process. So first thing to keep in mind is the ability to define something in an absolute sense is really just for convenience. Right? We don't need absolute quantities because all we're interested in doing is calculating changes in properties. Okay? When we define absolute quantities, we'll define them in an absolute sense relative to some standard state, some standard of zero which we'll define. And so when we take differences in these absolute values, that standard state will cancel and things work out all the same. Okay? And if you look at your steam tables in the back of the book or think about your first thermal course, we tabulate values of H and S, say in the back of those books. Right? We use absolute values because it's convenient, right? Rather than writing H minus H naught and defining that H naught in some way. Right? We just take H naught and S naught to be zero at some condition, and that's typically listed at the front of the, say, steam tables in that case. For water, common conventions, water at its triple point. So just to kind of go over where these things come from or how we can define these absolute quantities, is imagine, all right, I want to calculate some thermodynamic, let f be some thermodynamic state function, so I want to calculate an absolute value of f. Okay, so I'm going to use my favorite mathematical trick, and I'm going to add 0. So I'm going to say f is equal to f plus f naught minus f naught. All right, f naught minus f naught is just 0. Anything plus 0 is that anything. And I'm going to rearrange this to be f minus f naught plus f naught. Okay, so if I go to the next line, right, I have f is equal to f minus f naught plus f naught. Okay, cool. Now if I were actually to calculate this, okay, this term here, f minus f naught, right, I would break up in that f I could write as f ideal gas plus f residual. Likewise, f naught is f naught ideal gas plus f naught residual. So f, I'm going to write it as f minus f naught ideal gas plus f minus f naught residual. Okay, plus I'm going to leave this later one just as f naught for now. Okay, all right. Then we're going to look at, say, I'll call it convention 1. Okay, so convention 1 introduced in the book. Okay, so convention, and that wasn't a disaster. So convention 1 in the book, they call it defining essentially an absolute zero, so absolute values. Okay, and so in the absolute sense, what we're going to do is we'll define f to be equal to 0 at some conditions. So if you think of the steam tables, at the triple point, the enthalpy and entropy of water are taken to be 0. Right? So we define f naught as being equal to 0. So then I could calculate f as just f minus f naught ideal gas plus f residual minus f naught residual. Right? So f would be calculated as such. Okay, how does that make things easier for us? Well, if you think about enthalpy, okay, so enthalpy of an ideal gas, say, is just dH ideal gas is Cp dt. Okay, so if I want to calculate change in enthalpy, so H minus H naught ideal gas would just be integral from whatever my reference state temperature is to my temperature of interest, Cp ideal gas dt. All right, so this ideal gas term I can readily calculate. So if you look in the back of your book, there's some polynomial expressions for the ideal gas heat capacity. Then when it comes to the residual term, right, I can analytically evaluate those two terms using favorite cubic equation of state or corresponding states theory, so the Kessler tables. Okay, and so these terms then, all right, I have analytic expressions that I can readily use to evaluate them. Okay. Cool. If you had entropy, right, it's similar in that I could work out the differential for enthalpy, or entropy would be what Cp over T dt minus 1 over P dP, right? But I could analytically integrate said expressions with an expression for heat capacity. Convention 2 used in the text, okay, I'll call it convention 2. Okay. In convention 2, rather than say that F naught is equal to 0 at some reference conditions, it'd be that the ideal gas, so F naught, so the ideal gas value at that reference state condition is equal to 0. Okay. Well, how does that help me out? Okay. Well, we had, I just scroll up just a tiny bit, F is equal to F minus F naught ideal gas plus F minus F naught R. Okay. Well, F naught I can write as F naught ideal gas plus F naught R. Okay, so that gives me then, if I just expand this out, I have F minus F ideal gas plus F minus Fr plus, right, this is F naught ideal gas plus F naught R. Okay, well, we just took F naught ideal gas to be equal to 0. Okay, let me fix this up. That's Fr minus F naught R. Well, that F naught R would cancel with this positive F naught R. So I'll kill those. And I'm left with F is equal to F minus F ideal gas plus Fr. Okay, so again, this difference, right, I can readily calculate using our expressions for an ideal gas. And then this residual term here, right, this would just be now Fr. We have analytic equations from our cubic equation of states or corresponding states theory. But what's important is we have ways to calculate that. Okay, and so those are the two different ways that we can calculate, or two different common reference states that we can use to define essentially absolute quantities, right? They're absolute, but they're relative to some reference state, and there's the two conventions typically used to defining said reference states.